Okay, so let's begin from yesterday onwards. This is today's plan, but I want to show you the first two lectures again. So we'll take 5 minutes for warming up and then we will plunge into this. The first thing we talked about was what were algebraic schemes over a base field, and affine locally there are spectra of finite type K algebras. Our field K was arbitrary. And to such algebraic schemes, which we'll simply call schemes, and their morphisms over K, which we'll simply call morphisms, we want to functorially associate a kind of homology theory. But that question was loud enough. Rest of it. Okay, alright. So we want to associate to such data graded abelian groups. This is a kind of homology theory for such schemes, and graded homomorphisms between them, which will arise from morphisms of those schemes. Morphisms, I remind you, are always over the base field. And then we started setting up such a theory. In any such homology theory, the first idea is what are the cycles? And the cycles for this algebraic homology theory called Chow groups came from closed subvarieties. So every closed subvariety defined a certain cycle, which we, if the subvariety was V, we denoted the cycle by square bracket V. And a general cycle is a formal linear combination with integer coefficients of such basic cycles. So it's a free abelian group on the closed subvarieties. Now the closed subvarieties have dimension, which is why this is a graded abelian group, graded by the dimension of those closed varieties. And I also told you how closed subvarieties of a scheme are in bijective correspondence with points of the scheme. Given any point, you take its closure, give it the reduced-induced scheme structure, and that is the closed subvariety. And the point is the generic point of that closed subvariety, giving the backward transition. So, after setting up algebraic cycles, we wanted to talk about their equivalence, and the equivalence is going to come basically from rational functions on varieties. So, given a rational function on a variety, it has a certain locus of vanishing, perhaps certain locus on which it has a pole, need not be disjoint. Take the rational function x upon y on the plane. 0 along the y-axis, pole along the x-axis, and x and y intersect. Yeah. So we want to understand where a function vanishes, rational function vanishes, or has a pole, and of what order, and then count that and attach a cycle to it, which is of codimension 1 in the variety. So for that we need to understand the order of vanishing. And to do this order of vanishing, we began with discrete valuation rings. So actually we began with holomorphic functions and the order of a 0 of a not identically 0 holomorphic function. And then for this was additive with respect to multiplication. So it defined something on the quotient field also in a well-defined manner. To f upon g, the order is order of f minus order of g. The answer can be negative. There can be a pole. So this was for discrete valuation rings. And then we made the observation that this order of vanishing can also be characterized in terms of length of a certain Artin local ring which arises by going modulo that function whose order you want. And so we generalized it to one-dimensional Noetherian local domains, in which if I take any non-vanishing element, then the quotient by the ideal by that is Artin and so has a length. And that's the order of vanishing. And this generalized it from complex analysis and discrete valuation rings to all one-dimensional Noetherian local domains. Now such one-dimensional Noetherian local domains will arise if I have variety and a codimension 1 subvariety, and I look at the stock at the generic point, because then it has dimension 1. But remember, it's not a finite type K algebra, need not be, okay, in general. And so, but we never needed finite type K algebras, we only needed Noetherian local domains. We need something extra today about them, that is also true. And therefore, one can talk of the order of 0 or pole along a codimensional subvariety. And then we talked of examples such as take the function y minus x square. What is its order of vanishing along the x-axis? This is the kind of questions we asked. And then that led to the definition of the Weil divisor of a rational function, a Weil divisor. I'm not sure how this word is pronounced ever. Weil?
Way.
Way. That's your way. But so we talked about Weil divisors of rational functions on a variety. And then that led us to the definition of rational equivalence. These Weil divisors are what are equivalent to 0. And then two cycles are equivalent rationally if their difference is a linear combination of Weil divisors. All this in codimension 1, very easy. If the dimension of the cycle is less in a variety, then you want closed subvarieties of one dimension more, and on that a rational function. And a number of such closed subvarieties of dimension 1 more and rational functions from them, and then take their Weil divisors, add them up, and that's equivalent to 0. So once you go modulo that equivalence on this graded group, and remember this equivalence, all those are of the same dimension. So the quotient is again a graded group. If I take a graded group and if I take a subgroup, that doesn't mean the quotient group is nicely graded. But if your subgroup is also a graded subgroup, meaning it is a sum of its components. And so the quotient is again graded, and that's our Chow group. And then we started talking about how the Chow group looks. We said the Chow group vanishes beyond the dimension because there are no cycles simply. And below 0, again no cycles, except 0. Then we talked of Chow group of an affine line. We talked in general of Chow group of any algebraic scheme, and we said that the top Chow group at the dimension is a free abelian group on the irreducible components, or the cycles defined by the irreducible components, because there is nothing higher to induce any equivalence between them. So for an affine line, the first Chow group was therefore Z, generated by the cycle of the affine line itself. And the 0th one we said is 0, because given any closed point, which is a subvariety of dimension 0, we said that it is defined by the vanishing of exactly one polynomial. Polynomial is of course a rational function, so the divisor of that is this point. So all your basic cycles are equivalent to 0 rationally, and so the 0th group is 0. And then we talked about Chow group of affine spaces. So we said the top group is Z again. We talked about the 0th group, and we said given any point there is an affine line through it, and one of our friends gave a nice example in during the discussion hour, which showed that that point you may need an affine line which may not be defined over K itself, but may be defined over a finite extension. His argument, if some of you missed it, was suppose your field was Z mod 2. Then in A2, yeah, tell me if I am not correctly repeating. Then in A2, there are 4 K rational points. K is F2. And 4 K rational points, and a K rational line should have 2 points. Any line is determined by 2 points is what Euclid told us. So there are 6 K rational lines, because there are 4 K rational points. These 6 lines have lots of close points on them, but A2 is the closure of all its close points. The set of all close points is dense in A2. And so if all those close points were to be divided into these 6 lines, then the closure of the 6 lines would be all of A2. So, but all these lines are already closed. A2 is not, A2 is irreducible, it cannot be union of lines. Therefore, there are close points on A2 which are not on these 6 lines. Take one of those. Now if you take one such point, it's not K rational, it's not on any K rational line, but Hilbert null Stensatz tells us that whatever residue field it has is a finite extension of K. And so you have a line through it defined over that finite extension field F. So call that A1 over F. Now our argument that any point on a line or a field is rational equivalent to 0 now applies to A1f also. So there is a rational function on A1f, which is actually a polynomial in ft, and whose divisor is this. So the subvariety one dimension extra required is an affine line over an extension field, which is going and sitting as a closed subvariety here. Okay. So this is how we took care of Chow group of zeroid Chow group of any affine space. Then we talked of Chow group of projective line, and there again the first Chow group was Z because it's an irreducible variety, so its top is generated by itself as a cycle, nothing higher to kill any multiple also, so it's a free group Z generated by that. And the zeroth one, very interesting, we saw that whenever we have rational function, its Weyl divisor had degree 0. Any point has a degree, the degree of its residue field. If you are over an algebraically closed field, then you will say that a rational function has as many zeros as poles counting multiplicity. Okay? But here you just don't have to count multiplicity. Along with multiplicity, you have to also count the degree of the point. I might have the real line and I might have the function x square plus 1. Okay, it vanishes somewhere and that point has degree 2. So it doesn't vanish at two different points. It vanishes with multiplicity 1 at a degree 2 point. So you have to take into account both degrees and multiplicities, and then the divisor has degree 0 on P1. So this you know as a basic algebraic fact. Prove it for a polynomial, because for a polynomial the number of zeros counting multiplicities and degrees is the degree of the polynomial, and at infinity it has pole exactly that degree, and anything is a ratio of two polynomials. So prove. Okay. So this showed that the zeroth Chow group of the projective line is Z, generated by a point of degree 1, and for which we took the point at infinity, which is of degree 1. Yeah? Then we started the business of comparing Chow groups when there are morphisms. So we took a proper morphism and we introduced the notion of a proper surjective morphism of varieties. The degree of such a thing we introduced in many different ways. Number of inverse images of a general point, degree of extension at the generic point. We talked of singular homology, we talked of de Rham cohomology, all kinds of things we talked, and we said how this degree of the map is defined in this different context and gives the same answer we tested in some examples. Okay. So with that we were ready to define the notion of a proper push forward on cycles. And how we did it was, we took the cycle defined by a closed subvariety V, and we took its image, and that we made a closed subvariety of the codomain because this map was proper, so the image was closed. We gave it the reduced structure, and if the dimension was the same, then the field extension of the rational function fields was a finite extension, and that degree we took as a multiplier to the cycle defined by the image. If the dimension had reduced, then that degree we put 0. And so, having defined this proper push forward on basic cycles, by linear combination, it uniquely extends to the free abelian group. This is the universal property all the time of free abelian groups over a set. Do anything to the set of generators, set theoretically, meaning send them anywhere into another abelian group, and then there is a unique group homomorphism. Okay, making the triangle commute, that's the universal property. So we have proper push forward on cycles. And for example, if I had a curve, or if I had any variety which was proper over K, and I took a 0 cycle and I took its proper push forward, that's going to be the degree of that cycle. And then we came to discussing proper push forward for principal Weyl divisors, because remember our task is to show that this push forward operation that we have defined at the level of cycles goes down to the Chow groups. So it has to take rational equivalence to rational equivalence, which means it has to take rational equivalent to 0 cycles to rational equivalent to 0 cycles into them. Then it will descend to a graded homomorphism, grade degree 0 between the quotients. Now rational equivalence is basically generated by taking a variety, taking a non-zero rational function on it and taking its weight divisor. More complicated one are combinations of these. So if we look at one basic such thing, we want to show that it gets pushed into something that is rationally equivalent to 0. So that is what we are going to prove. That is the program for today, and we will finish proving it today, and then we will set up the problem for pullbacks. Okay. So that depends on how much time is available for pullbacks, because that's not serious. I want to take my time and explain this to you. Now let me tell you that in the things that we will do today, a certain amount of very simple commutative algebra will be used, which is explained in great detail in my written notes. So here I will explain the ideas philosophically why this works, but you have to read the proofs in detail there, close my notes and try to write the proofs in your own words and rinse and repeat. Meaning when you get stuck, open and look at it, but then close it and write it again till you are able to write those algebraic lemma proofs by yourself. This is needed. This is under the bonnet of the car. The car doesn't work without the engine under the bonnet. So though the commutative algebra is going to be under the bonnet, because I have a lot of geometry to go to, you are supposed to open the bonnet and read it and master the mechanics of it. Okay. When the car doesn't work, you shouldn't be helpless. And you should know that what I can tweak, and if my starting conditions are a bit different, oh, I know how that lemma was proved and I can make it work even this substituted by this and I get this, that is enough for me. This kind of arguments you have to do in serious algebraic geometry. So you cannot come with a ready-made packaged commutative algebra. You have to be able to open the bonnet and look at it when needed. Yeah? Okay. So let's go begin the business. So these are today's slides. We are going to first talk of different cases of this push forward, because when I have variety V and a rational function on it and I am taking the push forward, what if the variety goes down to something very tiny? Then the codimension 1 in it will also go down to something very tiny, and then the direct image is 0 as cycle. So if my variety is of a certain dimension d, the while divisor is supported on d minus 1 dimensional closed subvarieties there with plus coefficients for zeros and minus for poles, and it is those which are going down. If they go down to something of their own dimension, there is then non-trivial problem. But if they go down to something smaller dimension, some of them may go to the same. If they go to a smaller dimensional thing, the cycle is physically 0. No problem left in proving that it's rationally equivalent to 0. So therefore, we have to make cases which are dependent on dimension. So if the overall dimension decreases by 2 and you have a divisor in this, its image is at the most a divisor there, so its dimension has also decreased. Or its dimension may be everything. In that case also it has decreased, because the subvariety may map onto the codomain surjectively. But that's less by 2, this was less by 1, so dimension decreased. So whenever there is a definite dimension decrease from the codimension 1 subvarieties of the domain to their images, which may be codimension 1, which may be codimension 0, which may be smaller. But if there is a definite dimension decrease, cycle is 0. So no dimension decrease is what we are looking at. And when can it happen that no dimension decrease? A variety of a certain dimension, its image is of the same dimension, and a divisor here is going to a divisor there, no dimension decrease. This is serious case, both dimensions same. Or the dimension of the codomain is 1 less. Now I have subvarieties of codimension 1. They may be going and surjecting on that downstairs thing. Then again I have to seriously consider, what is happening. They might Is the cycle going to something 0? Or they may be going to something codimension 1. Okay, so that's why we are going to make cases by dimension. Some of those are, okay, all right, we'll see. So codimension 0, or relative dimension 0, relative dimension 1 are the only things that are going to matter. So that's why these cases push forward where relative dimension is 0, push second page of that. Then when the relative dimension is 1, it's as if it's like a curve. A curve is one-dimensional over your base field. When you have morphism of relative dimension 1 of varieties, if I go to the generic point there, its inverse image is a curve. So it becomes the case of a curve. So the codimension 1, or rather relative dimension 1 case, we will tackle through dealing with curves. But these curves will be over a new function, new base field. And so for that, as I said just some time back, direct image to spec k of a 0 cycle is the degree of that cycle. So we have to be able to talk of degree of Weyl divisors on complete curves. For P1, that degree is 0. We just now said that. Okay? But it's also true for any curve, any complete curve. If I have a Weyl divisor, its degree is 0. We'll have to prove that algebraically. And so once we do that, we are able to do it in relative dimension 1, and that will be the end of the proof of Chevalier's theorem, that rational equivalence goes to rational equivalence. And then we'll begin on flat pullbacks if time permits. Okay, so at this stage, so I have taken a long time to set up preamble. That is the purpose of an actual workshop like this, that you can take time and set up why you are doing it, what is important. Otherwise, if you try to read the book, and which you have to, the author doesn't have time. After all, what I am talking about is chapter 1. He has a very long way to go to cover very non-trivial material, so he is going to rush through that chapter 1, leaving so many things unstated, and even if stated, hurriedly stated and quickly proved. And well, anyway. So you have to read this and ask us questions this week, next week. Questions may come later as you digest it. Questions can come even later by email. Yeah, everything is allowed. Alright, so let's go to the material. So I have already talked about all this, why we have made these cases. If it has dimension n minus 1 less than equal to -2, then what happens? It's physically 0. Same dimension case and dimension 1 different case. So same dimension case is what we are going to treat. So perhaps the names may change. Now, to treat this same dimension case, there is a basic algebraic result that we will use. This is explained in great detail in the notes. The proof of this depends on earlier results and whatnot in the notes. But I am going to explain this to you qualitatively to make it look plausible. Why one should expect? What is happening there? So the idea here is the downstairs space, the downstairs variety, the codomain of the same dimension. I am going to go to its generic point and look at its ring. This is happening for the image of the Weyl divisor. So those are codimension 1 subvarieties. There I am going to the generic point of that codimension 1 subvariety, and there I get a Noetherian local domain of 1 dimension. So these Noetherian local domains that you read here, so you see W is the image of F, and then there are codimension 1 things in V mapping to codimension 1 things in W is the case we are considering, and A is the local ring of one such, and it's a Noetherian local domain. It's a technical requirement, and I'll soon tell you why I want that its integral closure in its quotient field should be finite over it. This requirement is satisfied exercise by all localizations of finite type K algebras. First of all, this finiteness of normalization is a very important thing in algebra and algebraic geometry. And there is a great tool which allows us to easily prove it for finite type K algebras or their localizations, and that's Noether normalization. So you have to use Noether normalization skillfully and show that, yeah, the normalization is indeed finite. When is normalization finite? Otherwise, without this finite type K algebra, essentially finite type K algebra, there are theorems. Kurulla, Kizuki, whatever it is, they are called various things, and they are not easy theorems. So it tells you that finite type algebras over K is much better than Noetherian local domains with some added conditions you may slowly put. So to do algebraic geometry, really finite type K algebras are ideal. But since you need to know more things, then you have to go on putting conditions on the rings. Alright. So this is going to be automatically satisfied because A is going to be the stock at the generic point of a codimension 1 subvariety of a variety, and that is essentially finite type over K because it's localization of a finite type K algebra, and then by using Noether normalization, its normalization is going to be finite over it. Now why do you want normalization and why do you want it to be finite over it? Let me quickly say this. We began the whole idea of order of vanishing by appealing to discrete valuation rings. And over discrete valuation rings, it's very easy to do your local algebra. Now, if you have some one-dimensional domain, which is not a discrete valuation ring, you take its normalization. It won't be local, it will be only semi-local. That prime will split into a number of primes. This splitting of primes is what all of you must have studied in your MSc level algebraic number theory courses. All the time they're interested in splitting of primes, right? And such issues, normalization, finiteness, whatnot. Okay, so it's a semi-local ring, but its localization at each one of those maximal ideals is a discrete valuation ring because it's normal. A normal Noetherian local domain dimension 1 is a DVR. So they are discrete valuation rings. So up there talking about order of vanishing etc. is very easy because they become discrete valuation rings. And if you have discrete valuation ring, it's easy to do a certain amount of linear algebra using the valuation. I'll tell you exactly what. So if A is a DVR, and you take A to the power n and you take some map phi. Suppose it is generically an isomorphism, meaning you go to the quotient field, localize at the zero ideal, it's an isomorphism. Which means it has to be injective, distortion free, and so it has a certain co-kernel C, and this co-kernel is set theoretically only supported over the closed point, and so it's a finite and it's finitely generated, so it's a finite module, it has finite length, and you want to know what's the length of this in terms of this linear endomorphism. And the answer using this idea that it's a discrete valuation ring is, now when I have a linear map from A to N and A is a discrete valuation ring, and this is something part of your basic algebra MSc level course, where you are asked Zn to Zn there is a linear map, and then you are asked to choose a basis here and a basis there so that the map looks very simple. And how does the map look very simple? You choose one basis here and one basis there so that the map looks like diagonal and some zeros, and each of the diagonal entries perhaps dividing the next and so on, yeah? In your structure theorem for finite generated abelian groups, you do such things. So I can choose a basis here and I can choose a basis here, two different bases, so that this matrix becomes diagonal, and diagonal entries are powers of T, where T is the uniformizer here. So this with respect to one basis ui's and one basis vj, and then the matrix M becomes T to the power R1, T to the power R something, and no zeros because it is generically an isomorphism. So it becomes something like this. So what is its determinant? It's just add all these. And what is the co-kernel? Co-kernel everywhere is A mod R1, A mod R2, A mod Rn. What's the length? Sum of R1, R2, Rn. And what is that? The order of vanishing of the determinant. Now you may say you have taken two different bases, so how can you take determinant? What is this determinant of a matrix doing there? But if I had to have the same basis, this matrix will be further multiplied by an invertible matrix, and whose determinant therefore will be non-vanishing. So the order of vanishing of the determinant is as if the two bases were the same. So it's a coordinate-free entity. Determinant for that endomorphism, when both transmitting basis and receiving basis are the same, is invariant with respect to conjugation further, and so it's really an invariant of the linear transformation, right? So determinant of this n is the order of vanishing of that order of the determinant is the length of this co-kernel. So length of the co-kernel is achieved as a certain order of a determinant. Okay, got this point? How determinant enters length calculation. Now, next thing which we talked yesterday, what has norm got to do with determinant? Because when the situation is a field extension and you are multiplying by some scalar, the norm is the determinant of that linear transformation. Okay. Where does norm of an element enter the picture? So now one by one I am telling you how the pieces, how the principal actors in this equation come on the scene at least. So I want to know how much this element B vanishes. This is this length. B is not exactly a free module over A, you may say, but then B is a submodule of the function field L, which is a finite extension of K, and I can always choose a linear basis for L over K whose elements are in B. So it's almost like a free module, almost, not quite. But you may ask, okay, almost, what does it do to length? It leaves the length unaffected, because if I have a module, another module, a map, injective map, and the co-kernel is of finite length, then for an endomorphism of the middle module which preserves the submodule, the length of, and which is generically injective, length of the co-kernel here will be length of the co-kernel here, because the difference will be the index of this linear map on a finite length module. If I have finite length module, what's the index of any endomorphism? It's 0. Okay. So you know, for example, if I have vector space to another vector space and a linear map, vector space to itself a linear map, okay, how does the index behave? So everything alternating sum is the same, and dimension of V and dimension of V are the same. So dimension of co-kernel is dimension of kernel, right? Rn to Rn I have linear map. How are the dimension of the kernel and dimension of co-kernel related? They are the same. So when I go to index, index is 0. Okay? So I can approximate this B by a free module, and therefore my length for B is same as for a free module, which is L over K, that free module. But then you may ask, does multiplication by small b take B into itself? No, because the basis for L was a basis over K. So when I multiply by a B, denominators will come up. But this is finite rank. Finitely many denominators come up. I make a common big denominator and multiply by that. And later that denominator coming from A itself, I know what its length. I don't have to go anywhere. And then subtract. So such little tricks, which I already told you what are those, show that this length is a certain determinant, and that determinant really is for a basis of L over K and multiplication by B, and therefore that is norm. So this is why this takes place. Okay. Now, you might object that, but then your B was not your A was not a discrete valuation ring. You told us this argument for discrete valuation ring. So how do you handle that? The answer is, I go to its normalization, and there are a number of points, and there all localizations are discrete valuation rings. When I went to this normalization, that was finite over the base by my assumption. So this calculation done for discrete valuation rings, I can leverage and get this equality for any one-dimensional Noetherian local domain whose normalization is finite over it. So this is the explanation for this side. Why is this true? Why are these degrees coming in this order, etc.? The reason is this element B, we have gone modulo it, and up there B is a semi-local ring. So when I go modulo this, see, a semi-local ring is not the direct product of its localizations, no. But when I am going modulo this non-zero B in this domain, that by Chinese remainder theorem is going to become the direct product of take all those localizations at maximal ideals and go modulo B and their product. So this sum over this, all this is coming out of Chinese remainder theorem applied to B mod B localizations mod B. Now you may think, okay, so I have all those points and I have the order there, and then the sum of that order, this point has split into several points, and the vanishing has now got distributed into all those points. So yes, I can understand why you are summing up all that order of vanishing at these different points, because if something has by Chinese remainder become a direct sum of things, its length is the direct sum of the lengths. So I understand that summation taking the order locally. What is this doing here? What is this doing here? See, what is happening is when your maximal ideal splits into these different maximal ideals, there are residue field extensions. And the residue field extension concentrates within it a whole amount of vanishing, which is the degree of that. And so you have to, in your count, multiply by that. If you remember how we are doing it on P1. How many times it vanishes and what is the degree of the point. And multiply those and add up over all those points. Then you get the degree. You have to multiply by this. Okay, that is exactly what is happening here. If you can separate these two things. You can say that, oh, I have a local homomorphism of Noetherian local domains. And I have a module. And I want to know what is its length below. So I take its length above. Is the length, so I have A to B, a Noetherian local or domain homomorphism. I have an B module M and I want to know its length with respect to A. So what do you think, its length with respect to A will be bigger or length with respect to B will be bigger? Length with respect to A will be bigger because B is already big. See, it's like I have real numbers to complex numbers. I have complex vector space. What is its real dimension? Twice. What is that? 2. The degree of C over R. You have to multiply that to get the thing there. Okay? So if I have a module which is of finite length, I manage to filter it. What is the only simple module over a local ring? Its residue field. So I got its filtration in which every step is the residue field. And so length boils down to adding up just the number of residue field every time. Those graded components are all residue field. So if I have the residue field upstairs, what is its length below? That's just degree. It's like asking if I have field K and extension field L and L as an L module, what is its dimension over K? That is L dot K. Okay? So at each individual Ni, this is what is happening, and by Chinese remainder, there is a sum. So I explained now this equality. Earlier I had explained to you this equality 5 minutes ago. So this common term can be written like this, can be written like that, and therefore this is equal to this. Yeah? Now I apply it to something in the function field. So it's B1 upon B2 kind of element. To that the middle term is absent. That B1 upon B2, that's no more an element of. But I have one such equality for B1, another such equality for B2. Forget the middle term and subtract those two. And then you'll get this. R is B1 upon B2. Okay? So yeah, Clear? Okay, good. So any questions? I'll wait for a minute. I have finished so far the first slide, my usual policy of 10 minutes per transparency. For lecture number 3, I have taken more than 40 minutes to finish the first transparency. A slow enough start, so I recalled what we were doing, why we were doing it, and I explained to you in detail why such a lemma works, why such an algebraic proposition works, what goes inside it. All kinds of integrants from orthonormalization to norms to anything. Very nice, different elementary algebra comes together and then you have this. Yeah? So should I change the page? Okay. So now let's apply it. This is the relative degree 0 situation of our theorem. So now I'll change names. I'll call my domain variety X. I'll call my codomain variety Y. This is a proper surjective morphism and both the dimensions are the same. I'm sorry, as I typed the thing, sometimes I called the dimension D plus 1 and D, or sometimes I called it D and D minus 1. Keeps changing. I think, okay. I will at some point, incorporating various corrections, suggestions, whatever, I'll issue a final one for the web page of INSEAM, then I'll try to make the notation consistent. Okay. So, I have this, both have dimension D, and I have taken a rational function, non-zero rational function, this is the multiplicative group, and we are going to show that the direct image of this Weyl divisor is the Weyl divisor of the norm, and therefore it is itself rationally equivalent to 0. And therefore, direct image of a Weyl divisor is rationally equivalent to 0, which is what we want to do. So, if I have taken, so where does this F lower star R sits? It's supported on codimension 1 subvarieties there. Okay. So, take various codimension 1 subvarieties. And now I am going to look at one of them at a time. So, I take one codimension 1 subvariety. And I take the local ring at this generic point. This is a one-dimensional Noetherian domain. Its quotient field is the function field of Y. Its restrictive field is the function field of W. So that is my ring A. And this is essentially finite type, localization of finite type K algebra. And so its normalization is finite over it. And so that last lemma, last page is going to apply to this. And what is B? So, now you take base change to this spec A. So, now we are considering a scheme which is not of finite type over K. Okay, I told you that scheme will mean finite type schemes over K, but sometimes not, and then I will point it out. So, now here is a scheme which is not finite type over K. Okay. So, I base change to it, and if I take a proper morphism, proper surjective morphism, and take a base change, I will get a proper surjective morphism. So, I have this proper surjective morphism. Y prime from Y prime is spec A, and that base change I called F prime from X prime to Y prime. So then X prime is integral. You see the generic point of X is already in X prime, and which is dense there therefore, and so it's irreducible. And X prime to Y prime is quasi-finite and surjective. You understand this word quasi-finite? In set theory there is something called finite, but in algebra, in fields, in algebraic geometry, a point spec L or spec K, issue comes what is the degree of the field extension L over K. That also you will demand to be finite. When you count the number of zeros of something, you count the degrees also, not just set theoretically. And so a quasi-finite morphism should have not just finite fibers, but finite residue field extensions everywhere. So fibers are set theoretically finite and finite residue field extensions, and therefore the base change to point is a finite morphism, so to say. When this happens, okay, the morphism is a finite morphism. This is a condition pointwise below, right? So I have proper morphism, that's not a pointwise condition, but this quasi-finite is a pointwise condition. When that happens, the morphism is finite. Saying that a morphism is finite means, if below I take an affine open subscheme, its inverse image, so call it spec A, inverse image is spec B where B is a finite A module. It's a finite algebra over A. You call such morphisms as finite. So here I am hand waving. Why it is so? Because this proof will really take us far. This involves what is called ZMT, Jaisky's main theorem, and so on. So these are issues which will take us a bit far afield, and so I have given you a reference. This is a good reference. If you read French, go read EGA, but otherwise, that's no joke. That's what we did for all these years before such English things came up. And even now, this stack project is rather overwhelming. There's so much of it. It's like you ask for a glass of water and somebody says, hey, here are Niagara Falls, go there. So you go with your glass to fill it under Niagara Falls, and you, glass, everything, go on away. Okay. So Stacks project is a bit like that for me. If I want to find something really, it's like drinking from a waterfall. So EGA being around for very long, and it's not as encyclopedic as this now. So, all right. So what are your references? Or there are modern textbooks. Surely there are modern textbooks which do such things.
There is a comment to this book by Iverson, very small.
Yesterday also I gave reference to Iverson because somebody wanted to understand Borel-Moore homology. And so I said, no, this is another Iverson. This is Berger-Iverson.
The same Iverson, but the book is called, I think, Generic Local.
Yeah, so I'm saying the same Iverson writes on all such things.
Of course.
This is also exercise in maximum. This is time factors.
Okay. This you can use, that's Stein factors. Anyway, so you can fix this the way you want, okay? All right. If you want to make quasi-projectivity, that kind of assumptions, projectivity assumptions, then things become much easier. Here is no mention anywhere of projectivity. All right, so as I said, these are issues we will leave, and so this morphism is finite, and that produces B. Therefore, X prime is spec B. That is the B. A was the local ring at the generic point of a codimension 1 subvariety W of Y, and now over that local ring there is a ring, and that ring is B, and that ring is an integral domain and it is finite over A. It's Noetherian domain, not local but semi-local finite morphism, and to this that proposition applies. So the closed subvarieties Vi of X which map to W are the maximal ideals. They are the close points in this Weistinch. And under this situation they contract. And these are the residue field extensions, the B mod I. And so from the algebraic proposition, the coefficient of W in F lower star R is norm X over Y R. Let's go back 2 steps. This side is going to be the coefficient of W by definition. Okay, and this side is so when I take the Weyl divisor of R, these orders come up, and when I take the direct image, these degrees come up. So when I take F lower star of the Weyl divisor, the coefficient of square bracket W is going to be this. And so that is the right hand side order of the norm, which means the Weyl divisor of the rational function called norm. And so it's the Weyl divisor of something. Okay. So as above, this is the Weyl divisor of norm. And this holds for each d minus 1 dimensional closed subvariety W below. After all, the direct image of that cycle, d minus 1 cycle, is made up of with various coefficients of such W's. And for each such W, you get this coefficient. So the sum is going to be in rad d minus 1 y. Yeah? So we have finished proving that if x to y is a proper surjective morphism of relative dimension 0, and I take a rational function on x itself, then the direct image of its Weyl divisor is the Weyl divisor of the norm of that rational function regarded as a rational function on y. Okay? So this is the relative dimension 0 situation to be applied to v and w. We are finally going to talk of x and y as schemes. They are not going to be varieties. This x and y is now going to refer to various varieties which occur in a cycle and their image. So now let's go to the situation of relative dimension 1. But yeah, I didn't follow my usual custom. At this point, any questions?
We can go to the previous.
One more?
So why is this base change integral being covered?
Yes. So so it's reduced first of all because I have localized. If I have already something integral and I localize, it's still an integral domain. Yeah? And the generic point is there. So locally it's an integral domain and the generic point is already inside. The generic point of x is mapping to the generic point of y, which is the generic point of spec A, that is y prime. And its closure is all of x. So its closure in that sub is all of that. So I have got something which is locally an integral scheme and irreducible. Okay. Any other questions? No, this was the page about which it is. Even if you have further go back, I am ready to do it. Okay. So let's go to the relative dimension 1 setup. So here the lemma we want to prove is this proposition that if I have complete curve and if I have rational function, then its Weyl divisor has degree 0. Let me prove it for compact Riemann surfaces. Why not? So I have a compact Riemann surface and on that I have a monomorphic function R. So this compact Riemann surface is this R belongs to, and I want to show that it has as many zeros as poles, counting multiplicities. Now degree of the point doesn't matter, all points are degree 1 points, they are all over complex numbers. So I want to show it has as many zeros as poles, counting multiplicity. So how do I do it? You know, being a monomorphic function, its zeros, poles, etc. are isolated. Otherwise it would have been identically zero, this is non-zero. So you take these points, isolated zeros and poles, and make a little disk around them. C has an orientation, so you put a certain arrow, therefore the boundary also acquires an orientation as I explained to you yesterday. And I am going to look at the differential form df upon f. Locally, you know, log doesn't exist all over complex numbers, but locally this is like d log f. Choosing a branch locally in a simply connected neighborhood, I can write it as d log f. Being d of a holomorphic function, this is a closed form. That's a local property, being closed. You only have to check it locally. So locally I can write it as d of log f, and therefore d of d log f is 0. So it's a closed form. Therefore I know that now I am going to integrate this on, I have this disk d1, d2, blah blah blah. So I have C minus union of di. This is a manifold with boundary, and I am going to integrate it on this boundary di. This joint union of the di's with appropriate orientations. And you know, if I have one form and I am on the surface and I am integrating it on its one-dimensional boundary, that's the same as integrating the d of that form on the two-dimensional one. What is this theorem called? Stokes theorem. So therefore this is going to be equal to d of df upon f on C minus this union of ds. So there you remove the open disks. I want a manifold, doesn't matter. Integral is going to give the same answer. And this is therefore 0, because this term is 0. log f locally. Therefore, this is 0. And now choose a complex coordinate z in this, around this disk. And so what is the integral of df upon f? Some 2 pi will come, eh? So it will be 2 pi I times the order of the 0 or pole. Am I right? Because that's your Cauchy integral formula, whatever, right? So this integral around, this is the sum sigma on individual di of df upon f, and that is equal to the order of 0 or pole, positive, negative, whatever it is, times the multiplicity of that 0 and pole, that is the order, sorry. And degree is always 1 here. So that sum is 0. So I have proved this result in complex analysis. Continuing with what we were doing yesterday, approaching the problem also topologically, also complex analytically, and also algebraically. Algebraically is the main thing, but you see why one expects this answer to be 0. Surely this argument must have been there before the algebraic argument, but then history is rather strange, so I can't be very sure what came first. So I want to tell you why this degree is 0 algebraically. So I can take the easy way and slightly less non-trivial way. Let me take the slightly less non-trivial way. It will go like this. I have this complete curve, and the slightly non-trivial statement is given any complete curve, it has a finite morphism to P1. It takes a little bit of algebraic geometry, ample line bundles, cohomology vanishing, and perhaps Riemann rock, I am not sure, to produce this finite morphism from any curve to P1. Once I produce this morphism, I have this Weyl divisor. I take its direct image on this P1, and that is going to be a Weyl divisor of the norm of that map by what I proved, relative dimension 0 case. And of that now I take the direct image. Direct image of direct image is direct image directly. This we saw already on cycles because multiplicativity of norm in a tower of field extensions. And so I take its norm on P1, that is already degree 0, so further direct image to or degree to spec k 0. But then where do I get this map? So now the more easy way. Suppose my curve was regular. Okay. Then every local ring is a discrete valuation ring, it's normal. And then if I take any rational function and I look at that missing point, because it's a regular ring, I can complete it to a morphism to P1 by the valuative criterion for properness. If it is that rational function is vanishing there, define the point to go to 0. If it has a pole there, define it to go to infinity. And this will be a regular function from curve to P1. Unfortunately, this argument doesn't work if my curve is not regular. Like we saw yesterday for the alpha curve and the function x plus y upon x minus y. It's not regular at that point, but it neither has a 0 nor has a pole. Okay? So now, simple, if your original curve was not already regular, go to its normalization. Pull back the rational function there. Normalization has the same function field, is birational. So take that function there, and now go to P1 and down, and you will have commutative normalization to original curve to point. Normalization to P1 to point. Everything being morphisms over K, this is going to commute. K is universal attracting object in the category of K schemes, right? So morphisms going to K, which are K morphisms, always whichever way you go, same thing, structure morphism. And so by these two steps, for the first step, normalization to P1, the same norm argument because it's relative 0. And then from P1 to down there, what we just now said. Yeah? So this is the proof that any divisor on a complete curve, any Weyl divisor of a rational function on a complete curve has degree 0. This is algebraic proof of what we proved analytically. See how different the proofs look and how the fact is the same. And so for the founders of algebraic geometry, people like Riemann, Poincaré and whatnot, they must have been in very exciting times discovering that what Riemann was doing is the same as what Kronecker or Weierstrass or people who used more analytic and algebraic methods were doing, what Dedekind was doing with Dedekind domains. And then everything put together in one common synthesis finally by Grothendieck and others, and modern algebraic geometers, because we should not forget the complex analytic and topological side of things. There is no replacing it completely by algebra. Okay. So, So have I justified this? Any questions on this proposition? We gave the algebraic proof, we gave an analytic proof in the complex case. ठीक है? And these are tremendously exciting statements. Looks like a simple proposition, but it's great fun. Seeing what goes into it, anything. Stokes theorem, taking log locally, simple connectedness, all kinds of things. So with this, we are ready for push forward of Weil divisors in relative dimension 1, because I have already explained how we are going to reduce it to a curve by Weil change, complete curve. Curve is going to be complete because my original morphism, relative dimension 1, proper. So base change proper, relative dimension 1, so that's a curve. So I have this proper surjective morphism. See, now its dimension has become d plus 1 and it was d on the last page, doesn't matter. So I take a rational function and this is its Weil divisor. And we want to show that it goes down to 0. We will show that it goes down to 0 physically. So, if I look at this V subvariety, this one, so these subvarieties are what support the Weil divisor, and their dimension is that of the downstairs one. Downstairs is one less, and these subvarieties are also one less, so they are of the same dimension. Now, two things can happen. This maps down to something even smaller, or it maps down to all of it. If it maps down to something even smaller, it's not going to get counted. So if the dimension is the same, then V to Y is generically finite degree. And so the quotient of Y coming from this V is going to be this. And if dimension is less, then this is 0. And so the total one is going to be F lower star R is sum of these which come from when the dimension is same times Y itself. So this sum I want to show is 0. And what is this sum? This sum is the degree of the Weil divisor on the curve that is over the generic point of Y. So we will evaluate this by base change to the generic point spec k of Y. And this base change is a complete curve, xk. That's the schematic fiber over the generic point. And that sits inside here, generic point maps to generic point. And this is an integral scheme by what I answered him some time back. And this is an isomorphism, the same residue fields at the generic points. And all those V's which were codimension 1 subvarieties in X which are mapping surjectively to Y become close points in this curve. They are dimension 1 less. Once you have got a curve, 1 less means they are close points, because the curve itself is 1 dimensional. So close subvarieties which are dimension 1 less, meaning 0 dimensional close subvarieties, is close points. So they are the close points. So the set of all close points of this base change curve maps bijectively to the set of generic points of codimension subvarieties that dominate Y. And so as a result, and okay, one has to also look at the degree. So the degrees are also going to be the same because the residue fields are the same. And so overall answer is the degree of this function restricted to this curve. The coefficient of square bracket y that you are calculating is the degree of the weight divisor on that curve. And that degree is 0, as we proved by the proposition for curves. And so, if I have proper morphism of schemes, and so it maps rat nx into rat ny. This was the remaining case, codimension 1, relative dimension 1. Earlier we talked of relative dimension 0, and before that we talked of relative dimension 2 or more, where it was trivially 2. So we have covered all the cases, and we have shown that rational equivalence is preserved under proper direct image of cycles. Okay. Okay, so at this point I ask you any questions. So this is the end of the discussion of the proper push forward. We have proved Chevalier's theorem that proper push forward preserves rational equivalence, and therefore, as we already discussed, it was already a functor at the level of cycles, and so it's a functor also now at the level of Chow groups. So,
the previous slide briefly.
Yeah, sure. Yeah.
Sir, when we are taking that base change with respect to that state, could you repeat why it is reduced?
Oh, you see, I have taken base change to a local ring, right? And there was some algebra over it, suppose. And I localize. Okay? This is a domain, and I have localized something.
So I was thinking, let's say, let's restrict this proper map to some state. And then if we are localizing that completely, we can look at it as a localization.
Yeah.
But it's not necessarily.
This is an injective map of domains there, no? And so I am localizing at something which are non-zero things.
Yeah, but there are various PIs which
No. That are after localization. We are localizing B itself now.
Okay, so this is after we have proved quasi-finite distance.
This, I have not localized at the individual ni's. This is localizing below. This A itself is obtained by localizing Y. No? See what this A, suppose Y was itself spec of R. Then that closed subvariety corresponds to a prime in that. And I am localizing R to RP. And R to S is an inclusion of domains. And now I am taking S localized at R minus P. And that's another domain, right? And C. Okay, this is very elementary algebra. You are asking really MSc level questions now. No? You realize? Yes, I have this inclusion of domains. I am not saying it is already affine, but take an affine open neighborhood here. And now you localize this at a prime ideal. Take an inclusion of domains and localize it at a prime ideal. It's a domain, yeah? The answer is clear to you. Now what's your other question? Why is it inclusion of domain? Yeah, because these are varieties. This is a proper dominant morphism, yeah, surjective, yeah, and of the same dimension. So generically it's inclusion.
Next slide now. This is kept for a while.
There is no substitute for homework. As I told you yesterday, you have to now sit tonight with the notes, the slides, and again go through it and come back with your questions if they still survive. And the discussion hours are there again. Okay. So the tutorial exactly is designed to answer this kind of question in this much detail. Okay. So let's move on, and I have 15 minutes now for 3 slides. Yeah. So I am going to set up some definitions before we go on. because I want you, as part of your homework, to recall a bit of flat morphisms. Hartshorne is not the best possible reference for flat morphisms in my opinion. Not very satisfactory on flat morphisms. Anyway, so, or smooth morphisms, it's even less satisfactory. So, morphisms have local properties. When I have two manifolds and C-infinity maps and I want to study local properties of these maps, that's called multivariate calculus. You do inverse function theorem, implicit function theorem, and all such local things. In commutative algebra, the analog of this are things called flat, étale, smooth morphisms and their various properties. A good old reference, where at least for my generation it was a good reference, was the textbook of Altman and Kleiman, Introduction to Grothendieck Duality Theory. This is an excellent basic text on flat, smooth, étale morphisms. Or I must say it was an excellent text when I was young. Today I find that it's not functorial enough. What you will like is formal criterion for smoothness, the lifting things, and things dealt with more via functors and universal properties, which that doesn't do enough. Altman and Kleiman were very young when they wrote this. If they rewrote it today, they will do a very different job, I'm sure. Alright, so somewhere you go read basic things about flat morphisms. Hartshorne plus, let's call it. Flat, smooth, etc. So first thing here is what's an equidimensional scheme. These schemes are again back to algebraic schemes over our base field K, finite type. So if every irreducible component which has a dimension, not all schemes have dimension, no? But algebraic schemes have, and if every irreducible component has the same dimension, then you call it equidimensional. This is how that is defined. And a morphism is said to have constant relative dimension if every fiber is equidimensional of that dimension. If some fiber is empty, that's allowed. Empty is supposed to have any, and is equidimensional of any dimension, because the demand that every irreducible component should have dimension blah blah is vacuously satisfied. There is no irreducible component. And we are going to talk of morphisms which are flat and of a certain constant relative dimension. So flat morphism, very easy explanation is in terms of the stock level map. I have point upstairs, its image downstairs, then from the local ring of the image point downstairs to the local ring of the original point, there is a local homomorphism of rings. That should be a flat homomorphism, means tensor product with that should be exact on modules over the base ring. Now, if I algebraic schemes, then this, and the morphism is flat, then this equidimension, it's enough to test it at close points. Flat is kind of uniform, and so if it happens at close point, it will happen around and so on. So I leave this as exercise to you. We are not going to use this exercise, just to make you feel more acquainted with this kind of stuff. Some fun exercising your skills. And so let's have a quick look ahead at what we are going to do. So we'll be interested in flat morphisms of constant relative dimension. I said for Chow groups we'll prove functoriality with respect to morphisms of various kinds. For push forward, we took any proper morphism. For pull back, we are going to consider flat morphisms of a constant relative dimension. Only those. The functorial property we will prove with respect to such morphisms. What about all other vast set of morphisms in algebraic geometry? How do Chow groups behave with respect to that? You will hear more about it in the succeeding lecture series in this. So for example, I might have something inside a larger variety, and I have Chow group and whatnot there, and I want to somehow restrict to this. Yeah, such things are also possible. And so on, so on, so on. So that you are going to hear in other lecture series. So I am going to talk about next pull back under flat morphisms of constant relative dimension, and that my course will end with that. Okay. So for such morphisms, first we will define a functor level pullback on cycles. That's relatively easy. So after defining this functor level map on cycles, then our job becomes to show that a rational equivalent to 0 cycle, if you pull it back, that pullback is also rational equivalent to 0. Now, this is not going to preserve degrees. The pullback is going to increase the degree by the relative dimension. So this f of a star is going to go from here to there. But it's going to be uniformly all the time d extra. So it's a graded homomorphism of degree d. Okay. There may be situations which we are not going to deal with where you have such pullbacks where the relative dimension is negative and it may lower things. Okay. We are not going to talk about that. So here this d is positive or 0 and it's going to increase. So this is a graded homomorphism and we are going to show that this defines a contravariant functor. So if I have two such, the composite pullback is going to be pullback of the composites. Both are flat of constant relative dimensions, but the relative dimensions may be different. So what is the relative dimension for the composite? Is the sum of the relative dimensions. This you can easily see from how we defined it. And so the pullback will be of relative of graded degree d plus e when the individual degrees, graded degrees are d and e. So once it defines such a contravariant functor, we want to show that it goes down to, okay, so here is some saying in great detail what does functoriality on cycles means. First of all, it says that identity should pull back, that pullback should be identity. Identity is flat of relative dimension 0 and the resulting pullback should be identity on the cycle groups. And the composite should be composite. This is functoriality. And then we will show that if I have something in what? Yeah, opposite direction always remember. So this rat ny is here, map is from x to y, this is here and then it goes into this. And that will induce a map on Chow groups. It is functorial because this is functorial. So this is what we are going to prove next. That's for tomorrow and part of day after tomorrow. Okay, so with all this, I have finished 7 minutes in advance as for both my last 2 lectures. Okay. Good, so that is comfortable. So yeah, now do ask anything. Nothing. All right, so we reconvene at 11:30.